Hi everyone! As you may have noticed, I recently released a new ebook that practically summarizes almost everything I've discussed here about creating shaders in Godot engine. And not only that, I've added a lot of additional information about the algorithms used and some theory on how shaders actually work. The book also includes the complete source code for all the shaders included. So, if you don't enjoy manually transcribing code from the video, you can simply use copy and paste. You can get the book in my eShop on Gumroad, and I include the link in the descriptions of each video from now on. And one of the topics I covered in the book is advanced post-processing, which will be the subject of today's video. You might be wondering why several upcoming videos don't include a promo for the new book and still display only the previous one about creating a space shooter. This is because I recorded some videos back in June to have content to release during the summer holidays, a time when I have many other activities. I recorded today's video just yesterday so that we would have something fresh. Alright, enough talking. What is advanced post-processing and how does it differ from screen reading shaders that I described earlier? So far, we've been dealing with post-processing using a 2D shader. This solution is simple and sufficient for many effects. However, if we want to fully utilize the capabilities offered by a scene with 3D objects, we need to use a slightly more advanced solution, post-processing with a spatial shader. This allows us to access features such as the depth texture and create effects like this volumetric fog. Okay, again, this is a scene from my experimental project, third-person controller, which you can download from GitHub. I achieved the fog effect by rendering objects closer to the camera more clearly than those farther away, and this is facilitated by the mentioned depth texture. However, before we start programming the shader, a bit of preparation is needed. Why is that? Unlike previous screen reading shaders, when we managed with a color rect, it is now necessary to apply the shader to a three-dimensional object that simultaneously covers the entire screen. For this, it is best to use quad mesh, set its parameters and add a special shader to its material. You can use any 3D scene, for example the mentioned third-person controller project, or just a brand new 3D scene. The following procedure looks like this. Let's right-click the root node, which is main in this case, add child node and select Mesh Instance 3D. Okay, now let's open it in the inspector panel and let's set new quad mesh to the mesh property. Quad mesh is right here. Click it and I will set size to 2 by 2. And another important property to set is flip faces. It must be on. Very well. Now I'll scroll down and create a new shader material in the geometry material override property. Here it is. Click and select a new shader. New shader, and here in this dialog it's necessary to have just a normal shader, not visual shader, and the mode must be spatial. I will just call it main GD shader, sure, why not. Create and click again to open it here in the shader editor. And there is one more thing, let's go back to the inspector panel and in the geometry section right here, let's find extra color margin and set the maximum value, which should be this one. Very well. Does this procedure seem complicated? It's actually a workaround that will hopefully be simplified in future versions of Godot. With this, we are ready to write the actual shader, which should have been open in the editor right here. Unusually, we will start by setting the render mode. I'll do it right here, and render mode is set to unshaded. Okay, what does it mean? Because we don't want objects in the fog to be affected by external light sources. We achieve this by setting the render mode to unshaded. Once we are finished with the entire code, you can try commenting out this line and see the difference. Okay, let's go ahead and add uniform parameters. First I will write them, then I will explain them. Uniform sampler 2D, and I'll call it screen texture, hint screen texture, this one, yeah, and filter linear map. Okay, the second one would be uniform sampler 2D again, depth texture, source color, and depth texture. Here it is. And finally, uniform float, this time depth range, which would have a hint range and the initial value set to 10, and the hint range would be from 0.1 to 100 and with a step of 0.1. Okay, so the first one, screen texture, is well known. It's a hint screen texture which contains the current frame for post-processing, and we know that from our previous videos where we've been doing the simple post-processing light edge detection or CRT monitor. This time we also added the parameter filter linear map, which should allow us to achieve a smooth transition between textures depending on the distance of the camera capturing our 3D scene. The second parameter, depth texture, has the value hint depth texture, and it provides us with access to the depth texture, of course, and will be the basis of the fog effect. Finally, we use depth range to set the distance from the camera at which the fog effect should occur. The next step is to ensure that the quad mesh is always displayed in front of the camera. We achieve this using the vertex function. Let's do it here, and it's just one line. We set the internal position variable to vector4, which have the vertex value and 1.0. Okay, now everything is ready for the implementation of the fragment function. We will start by reading both textures, as the resulting effect will be a combination of the original scene and the created fog. Then we will add both values and assign the results to the variable albedo right here. So let's do it and start with this. Vector2 screen UV is the internal screen UV. As you may remember from previous videos, we usually use just UV for let's say normal shaders, and screen UV for screen reading shaders that handle the whole screen or the whole viewport. Now we need to set the initial color. That would be, let's call it just vector3 color. And as I said, we combine both textures. So let's start with the screen texture and the coordinate screen UV. And we are interested only in RGB components, not the alpha value. And now we need the depth, and we'll take it like this. Float depth is, now we read the depth texture at the same coordinates, same coordinates, and take just the first component, which is either R or X. And now let's define the fog vector 3, which is simply vector 3 with all its components equal to the depth value. And finally, we need to assign it to albedo, which is different, like as you know from the canvas item shaders, we used color. In the spatial shaders, we used albedo. Is color plus fog. Very well. Okay, I will run the project and let's see the result. Okay, there are at least two issues. One of them is this hair. Why it is displayed this way and the rest of the body seems to be in the fog. Let's find out. Exit the project, and now I will switch to the character scene, and it seems that the problem was only with the hair component. If I switch here, we can see the character and the hair. What's wrong with that? Let's click on its material, and we can see that the transparency is set to depth prepass. This came from the Mixamo model for some reason, and it simply means that the depth texture is not aware of this particular part of the body, and the depth value seems not to be affected by that. So if we set it just to disabled and run it again, we should see that this problem is gone. Yeah, there is only the silhouette, which is barely visible, I guess. It seems that the result is quite overexposed. And the reason is that the values obtained from the depth texture are non-linear, so they only drop below 1 when they are very close to the camera. To achieve a usable effect, we need to perform transformations to a linear range, like this. Let me just switch back to the shader editor, and I will do the following changes. So we have color, depth, this is correct. And now we need to do this. Vector 3 and DC, I will get to the explanation shortly, is vector 3, screen UV multiplied by 2, and we subtract 1, and depth value. Okay, vector 4 view is inversion projection matrix by vector 4, which we composed of NDC vector and 1. Alright, and now we need to normalize that, so view X, Y, Z would be divided by view W, which is the fourth component of the four-dimensional vector. And now finally float linear depth is negative view Z divided by the depth range, our uniform parameter. And now we don't use depth here, but the linear depth to define the fog. Let's try it now. Okay, much better, and I would say it is basically the same as we had at the beginning of this video. The fog looks pretty normal and natural. Great. Okay, in the 4 new lines of the code that we added to the fragment function, we are doing the following. Where it is? Here. So we calculated the normalized device coordinates, hence the abbreviation NDC, in the range from -1 to 1. Then the linearization itself was done using the inverse projection matrix, which is the internal variable of this spatial shader. And finally, because the camera is facing the negative Z direction, the position will have a negative Z value. To get a usable depth value, we had to negate this one, negative view Z, to negate it to get the final value of the linear depth. Got a typo here, right? Linear, yeah, A. Okay. Is it too complicated? Don't worry about that. I'm not entirely sure if I understand all the details either. The important thing is that we don't actually need to fully understand it, because this approach will work every time we decide to create an effect using the depth texture. And what if we wanted to use a normal texture instead for rendering, which we also have available in the spatial shader? The code would look like this. So let's add one more parameter, uniform sampler 2D, normal texture with a hint normal texture, roughness texture, this one. And again, filter linear map. Okay, so we have the normal texture, and now we need to use it, and it is a bit simpler than before because I can get rid of all these lines and simply define the normal value, which would be vector 3. Normal is, and let's read the texture, normal texture, screen UV, and again RGB components. And now we simply add these two values. Normal, that's all. Let's take a look. And we can see the normal vectors or normals visualized in this RGB color space. Great. And finally, we also have roughness, which is contained as the fourth dimension of the normal texture, this one. Since it's a float value, we will use it by converting it into a three-dimensional vector before assigning it to albedo, just like we did with the fog value. So instead of normal, now we need just float. Roughness is texture, again from the normal texture, and screen UV, but this time we take the fourth component, which is W, and here let's create the vector 3 from the normal roughness value, roughness, and let's take a look. Yeah, completely different, and we can see how the roughness is applied on all the models, like just the character and the floor. Great. And that's all. In the book, I wrote at this point that we have just mastered the basics of advanced post-processing in the Godot engine, and it can be said that this is indeed the case, because working with depth and normal textures is crucial for this kind of effect. In the future, I would like to try creating slightly more advanced effects, such as enhanced edge detection, so we will return to post-processing several more times. For now, thank you for your attention. I wish you much success with your game projects, and see you in the next video.